Hey guys, this is video 4 in a video series on game theory, and in this video we're going to be talking about the key concept Nash Equilibrium. Now, full disclosure, the Nash Equilibrium associated with that game, the game we talked about in video 3, not that interesting. But here's the big deal. You are going to understand this concept by the end of this video. You're going to understand it well, and you're going to be able to figure out whether or not a game, any game, has a Nash Equilibrium or multiple Nash Equilibriums. I think that's called Nash Equilibria, but whatever. We're going to be able to figure out if a game has a Nash Equilibrium or multiple Nash Equilibriums. Now, let's get to this particular game and do a quick recap, okay? So what we have in front of us is a prisoner's dilemma. Basically, we have Fred and Jack. They have been committing major crimes and lesser crimes. They've been arrested. The state, or the police, if you will, they have the evidence to basically get a conviction on the lesser crime, but not the major crime. They need them to confess to turn state's evidence. Now, here's what we found in the last video. We found that they both have a dominant strategy. Now, what is a dominant strategy? It is a strategy that yields a superior result regardless of the strategy the other player played. So, just to kind of recap that very quickly, Fred, hey, he had a dominant strategy. It was confess. Why was that? Because if Jack did not confess, Fred, what would be better out of these two things? Not confess, 2 years in prison. Confess, 1 year. Confess was better. And if Jack confessed, Jack played that strategy, what was better for Fred? Not confess, 15 years. Confess, 8 years. Again, it was confess. Confess was a dominant strategy. It was a strategy that yielded a superior result regardless of the strategy the other player played. Now, this is a symmetrical game, and since it's a symmetrical game, that means Jack also has a dominant strategy, and it's the same dominant strategy, okay? So, confess and confess. Now, go to video 3, and you can see me analyze Jack completely. Again, we did that in video 3. Let's not do it now. Let's just say, look, we've got a dominant strategy and a dominant strategy, which means if they play in their own self-interest, they're going to land right here. But this video is about Nash Equilibrium, so we need to talk about that concept. Again, I'm going to say something I said at the beginning of this video. The outcome here is not going to be that interesting, and I'm afraid it might give you the wrong impression. It might make you think that Nash Equilibrium is not that important of a concept because it's already taken care of the dominant strategy, and that is not the case, okay? Nash Equilibrium can be very important, and it can be present in situations where we don't have dominant strategies. In fact, it's much more interesting in situations where players don't have dominant strategies, okay? But again, not that interesting for this game. Just know that as we go into it, but just understand it is so important of a concept. So here we go. Nash Equilibrium. When we do Nash Equilibrium, we look at Nash Equilibriums, guys, we don't start with strategies, we start with outcomes, okay? There are 4 outcomes related to this particular game. That's an outcome, that's an outcome, that's an outcome, that's an outcome. We start with a particular outcome, and we analyze it. So, we're ready. What is a Nash Equilibrium? It is an outcome, okay, for which neither player has an incentive to change their strategy given the strategy the other player played to get there. Whew, I know, that was a mouthful, so let's do that one again. What is a Nash Equilibrium? It is an outcome for which neither player has an incentive to change their strategy given the strategy the other player played, okay? Now, to fully understand that, you've got to see that put into practice. So that's what we're going to do. We're going to start off right here, and spoiler alert, that is a Nash Equilibrium. But that's where we're going to start, this cell, okay? That is an outcome, and we're going to analyze that cell because that's what we do when we're trying to find a Nash Equilibrium, okay? So, how did we get here? Confess, confess. They both played confess. So here's how we analyze it. We say, okay, we're right here, and now I'm going to do it kind of like from Fred's perspective, is I'm going to say, look, would it be beneficial for Fred to change his strategy given the strategy Jack played to get here? Jack played confess. Given that, would it be beneficial for Fred to change to not confess? Well, no. Okay, so again, I know this is kind of like, we're in the weeds, but we have to be in the weeds to understand this concept. We're doing Nash equilibrium. We go to an outcome. And what is a Nash equilibrium again? A Nash equilibrium is a situation where neither player has an incentive to change their strategy given the strategy the other player played to get to that outcome. So Jack played confess. That got us here. Is there any incentive for Fred to switch to not confess? 8 to 15. The answer is no. And that's what we're looking for, is no's. If it's a no, it might be a Nash equilibrium. You get 2 no's, it is a Nash equilibrium. You get a yes, you're done analyzing it, okay? So let's go to this one, okay? Look, does Jack have an incentive to change his strategy to go from confess to not confess, given Fred played confess? Given that Fred played confess, would Jack benefit from switching? The answer is no. He would go from 8 years to 15. You get 2 no's, and you have sorry about that. It's going to start the word equilibrium. A Nash, right? A Nash equilibrium. That's about as ugly as it can look, but you have found a Nash equilibrium if you get 2 no's when you analyze an outcome. So let's go look at another outcome. Let's take this one right here. Okay, is this a Nash equilibrium? Well, how did we get here? Not confessed by Jack, confessed by Fred. Okay, does either player have an incentive to change their strategy given the strategy the other player played to get to this outcome? So, given that Jack played not confess, does Fred have an incentive to switch from confess to not confess? No, he does not. 1 year to 2 year. No, so maybe it is a Nash equilibrium. But given that Fred played confess to get to this outcome, does Jack have an incentive to switch from not confess to confess? Yes, he does. Again, if you get a single yes, it is not a Nash equilibrium. Let's go to this cell. This one's going to be 2 yeses. I'm going to tell you that right from the get-go, okay? How did we get here? Not confess and not confess. Given that Jack played not confess, does Fred have an incentive to go from not confess to confess? From 2 years to 1 year? Yes, he does. Given that Fred played not confess to get here, does Jack have an incentive to go from not confess over to confess? Remember, given that Fred played not confess, does Jack have an incentive to change from not confess to confess? The answer is yes. 2 yeses, definitely not a Nash equilibrium. Final outcome, okay? Given that Fred played not confess to get to this outcome, does Jack have an incentive to switch from 1 year to 2 years, from confess to not confess? No, he does not. Given that Jack played confess to get here, does Fred have an incentive to change from not confess to confess, from 15 to 8 years? Yes, he does. Not a Nash equilibrium. I know, a little bit confusing. You get 2 no's, that's a Nash equilibrium. That's a situation where neither player has an incentive to change their strategy based on the strategy the other player played to get to that outcome. You get 1 yes, it's not a Nash equilibrium. Now, here's the thing. All equilibriums in economics is where we are gravitating towards. It's where we're pulled toward. So we can pretty much know in this game is pulling us here. That if this game right here is out there, the result we're going to get most often is going to be right there. Now, not that interesting for this particular game, right? And why is it not that interesting? Hey, dominant strategy, we already had that cell. Okay, so it's a Nash equilibrium, big deal. If both players have a dominant strategy, it's not that interesting. The intersection of the dominant strategy will always be the Nash equilibrium. But that Nash equilibrium gets really interesting when neither player has a dominant strategy, because then you can still have a Nash equilibrium, you can have multiple Nash equilibriums, and that is when it gets really interesting. Anyhow, I hope you've got it. One last time, a Nash equilibrium. It's an outcome in which neither player has an incentive to change their strategy given the strategy the other player played to get to that outcome. Hope that made sense to you. We'll see you in the next video.